Wait, so the marks the points that we're putting on here are going to be the predicted?
Yeah, that's the predicted line. There is a way to actually draw that in, but whereas you're not competent even getting the picture, I tried for quite some time ago, to actually get it to draw the best fitting line in this example, but I just couldn't get it to work, so I gave up. Yeah, a little paper, a little ruler, and kind of make that happen. So what you really want is you want as I said, you want the predicted value to be close to actually what you found in the original data set. Now these next two screens, once again, SPSS automatically computes these when it does regression, and it comes up with the best fitting line equation with doing a lot of math that your book describes. I see no reason to teach that, because if you just have your data set, you hit regression, and then it'll do all of this. So there's no reason to actually learn how to do, slope and intercept and all that kind of stuff. So a couple of important things for these two screens. These two screens are going to be very important for you. Let's actually go to the bottom screen first. Now, don't be too confused the fact that it does an ANOVA. You can actually do an ANOVA even if you've got regression. I don't want to explain why that's the case. What is the purpose? What do you think the purpose of this thing is? If you're doing regression, you want to see if this result is significant. Did we start? Yep. You want to see if your best fitting line is statistically significant. So the purpose of the ANOVA screen is basically to tell you, okay, we came up with a best fitting line. Is this line statistically significant? Can the X values predict the Y values? Can I use weight to predict snoring? So this ANOVA screen is going to say whether or not this variable predicts the other variable. How does it look at the end of this? Does it look good or does it look bad? How do you determine if something is significant?
It's less than 0.05.
If it's less than 0.05, what do you know? It's significant. So I bolded the 0.029, which basically means that this best fitting line is statistically significant. The way you would write this out, so let me tell you how you would write this out first. You write it out like an F statement. So F of what? Look at the screen. F and then in parentheses 1, 3 equals 15.5, comma P equals 0.029. This tells you that the regression line is statistically significant, that you can use BMI to predict sleep apnea. Go ahead, Tara.
Okay, and please forgive me.
No, it's okay. This is tricky stuff.
These errors look huge.
Yeah, these numbers look huge here. The question is the errors that we already computed.
Yeah, like the ones that we got.
Yeah, they seem pretty large here. Let's actually take that to another step, though. I asked you to square everything, right?
Uh-huh.
Now, maybe you can do me the favor and add up all those things that you squared. What did you get?
514.06.
So you got 514.
That's close to that residual thing.
Residual. As it turns out, the reason I had you do this for kicks, do you remember in the ANOVA screen, does the word residual sound like a good thing or a bad thing? Residual.
It sounds like leftovers.
It sounds like good leftovers or bad leftovers?
I'm thinking that looks like a whole lot of leftovers.
Bad leftovers. So residual is error. This is measuring the error. And so in fact, that's exactly where it comes from. This is measuring the amount of error in your equation. And that is 513. Don't worry about the degrees of freedom at 3, but the variance for the error was 171. That is error. But on the other side, there's how much can the regression equation account for. And because the correlation is so high, this best fitting line is really accounting for a lot. So the top line, the one that says regression, is good stuff. Just like the sums of squares between, we want that number to be large. That means our best fitting line is working well. The residual, you want that number to be small. That means the error is small. And so even though there was 513, comparatively speaking, the amount of error in this case, 171, to the amount due to the regression, this best fitting line is actually really good. It's very predictive. Now, I didn't show you how you compute the regression. There's a way to actually do it. But remember, we had a best fitting line. Remember what the correlation was. 0.91. Those points are pretty close to on a straight line. Although it looked a lot when we drew it because everything was so expanded. But if it was a really big scatter plot, it would almost look like all those points are right on a straight line and perfect. Remember what happened with the second value, the 15. We got a perfect prediction for that. So in fact, the amount of error here is very low. The equation is doing a good job. So if you get a large regression component and a small amount of error, that's considered good. What if it was reversed here? Yeah, if you get more on error due to regression, then you're going to get a low F-score. That's going to mean what for the best fitting line? That it's not accounting for anything and it's not significant. Finally, we got one more thing here. We got to go to the model summary situation. Notice what I bolded here. See the number I bolded here? The 0.784. Your book describes this, but I'm going to tell you kind of what this thing means as well. It's given a stupid name, but then again, this is statistics. It's called the coefficient, and you can look it up in your book, the coefficient of determination. Going to be a lot of downloading tonight. The coefficient of determination. How's that sound? Serious. But here's the real world statement for that 0.784. And you'll want to write this down properly verbatim. The verbatim statement is the following. If I know BMI, I can account for 78%. I can account for 78% of the variance in snoring. If I know this one variable, BMI, I can account for 78% of the variance in snoring. So I got one variable that can account for 78% of the variance. Does that sound good or bad? That's really good because the top number that could be is 100, right? So this is one variable that accounts for 78% of the variance. It's not saying I can predict this snoring 78% of the time, but I can account for 78% of the variance. That's really good. And it maps well to the bottom screen. Should one variable that accounts for 78% be significant? Yeah. That's a lot.
So you just want that to be as close to 1 as possible?
You want that number to be as high as you possibly can. The higher that is, the lower the probability in the next box is. But as you go on in your education, you may read articles where people do correlation and regression. You don't need to know the best fitting line equation, but they'll give you the adjusted R squared and whether it's significant. So you should be able to kind of understand these two things. Let's finish this off by just looking at the book a bit and the chapter on regression and seeing if it actually says anything that I'm talking about here. For the 9th edition on page 562, they actually show the distance between the predicted and the actual, which is what you want to be small. They do a lot of the math, though, and I'm just not into that so much. I don't think it's of value to you folks. There's another one a little later in chapter 16, it looks like on 566, that also shows you want a small amount of distance there. Let's see what else they have. If you turn to 571, and I think in the 8th version it's a figure where they partition the regression. They partition the regression. It's kind of like partitioning the sums of squares between and within. You want the amount that goes to the regression to be large,
It's on 578.
578, and you want the residual amount to be small. So it kind of works like an ANOVA. Aha! You have this picture in, this is on 573, boy, my eyes are going bad. 581? If you look at this situation, this is actually a multiple regression situation. You're trying to predict the DV as academic performance. What are the two predictors here? IQ and SAT. We're not going to do multiple regression, but that's where you draw out the circles. If you were to draw out the circles for this example, you'd have one circle, and then the other one would overlap it by 75%.
Because of our adjusted R.
Because of the adjusted R squared, exactly. If you look on 576, and here's a few more pages there, did they give you ANOVA summary tables? Or are they not so fun?
Is it on 586?
586 for you guys? This is on 576 for version 8.
There's a whole extra chapter we don't have.
Oh, so sad. Anyway, they show some F values there. They've got an F of 4, the probability of 0.058. So you can get SPSS printouts from this.
Do you want a picture of this?
Don't worry about it. It's just, it's not critically important here. So, from regression, hopefully what you understand is when you do regression, and I put the term, I did put it up there, coefficient of determination. Regression is the business of prediction. Use one variable to try to predict another one in simple linear regression. It's different than correlation. In correlation, what are we looking at? Your two variables, but the relationship. If you're looking at a correlation, you say, oh, there's a significant correlation as BMI goes up, so does snoring. But you don't say if it's correlation that this predicts that. That's regression. They're very related. When you do regression, you say this variable can predict that one. You look at the adjusted R squared. You hope the adjusted R squared, the coefficient of determination, is high. It's the correlation squared, basically. You hope the ANOVA is significant, and this tells you that this variable, BMI, is a significant predictor of the other. Comments or questions? Okay.